Hello everyone, welcome to Unfolding the Universe. I'm Ashley Zelinskie and we have some great people here today, including myself, because I'm going to be speaking instead of Sarah Kendrew today from the European Space Agency. Apparently she had a bit of a family emergency, so she's not going to be able to be with us tonight to speak about the MIRI instrument. But check back on her schedule because she is going to reschedule herself for one of the other weekends. But we do have Con Yang today. And he is going to be speaking to us about his work on the James Webb Space Telescope. And then when he's all finished up, I'll give a short artist talk to take up the remaining time. So, Con, you want to come up here? Nice.
Uh-oh, seen it all.
Well, thank you, everyone. Thank you for that warm welcome. My name is Con Yang. I am the team lead for the Instrument Design Laboratory at NASA's Goddard Space Flight Center. And today I'm going to be talking about the James Webb Space Telescope, and I'm going to provide a thermal perspective on NASA's engineering marvel. Before I begin, I'd just like to thank Ashley Zelinskie for setting up this amazing show and for helping us share the excitement of Webb. Your work is very much appreciated. Thank you. So just a little bit about myself before I begin talking about Webb. I was born in Beijing, China. I came to the US when I was 3. I grew up in upstate New York. I got my undergraduate degree at the University of Michigan, and then I went to graduate school at the University of Maryland. I chose aerospace engineering as my major because I've actually always been fascinated by space since the first time I visited an observatory when I was actually 6. And I joined Goddard Space Flight Center after finishing up grad school at the University of Maryland. In 2010, and I was a thermal engineer at that point. So I worked on a lot of things from satellites that track hurricanes to satellites that examine the dust environment around the moon. And currently I have a position as the team lead for the Instrument Design Laboratory. So what we do there is we design the next generation of instruments that Goddard will fly in space. My role on the James Webb Space Telescope was actually the lead thermal analyst for the telescope's cryogenic vacuum test, and I'll just talk a little bit about what that is in a couple slides. So first off, let me talk a little bit about the telescope in general, right? What is the James Webb Space Telescope? JWST is a mission to seek light from the first galaxies in the universe, as well as to explore distant worlds. We want to be able to observe the first luminous objects in the early universe, as well as the galaxy and stellar system evolution. And we want to be able to explore the solar system as well as exoplanets that are orbiting other stars. Now, observations on JWST, they're performed by thousands of astronomers worldwide, and it's optimized to observe in the near to mid-infrared wavelengths. So you can see the wavelengths there, 0.6 to 28.5 microns. Now, JWST is led by NASA, but this is also in a partnership with the European Space Agency and the Canadian Space Agency. Let's talk about who James Webb was. So James Webb was the second administrator of NASA from 1961 to 1968. He oversaw the first and second crewed spaceflight programs, so that's respectively Mercury and Gemini, and also oversaw the Mariner and Pioneer planetary exploration programs. He was also in charge of the Apollo program in its run-up to the landing on the moon, all the way up to 1968. And then he did always insist that NASA have a very strong science program. And it's his insistence of NASA's science portfolio that we actually have telescopes like the James Webb Space Telescope and, of course, the Hubble Space Telescope before that. So I just mentioned the Hubble Space Telescope. A lot of you are probably familiar with Hubble. It launched in 1990. And for any story about JWST, we really need to start with Hubble. So Hubble, after it launched, it took really amazing and revolutionary images of our universe. It allowed for groundbreaking discoveries in astronomy. It also confirmed the age of our universe at 13.7 billion years. It proved that the universe was expanding as well. And it gave us a really great window into the billions of galaxies in our universe. It showed that black holes were most likely at the centers of all galaxies. But as with any science instrument, it, especially being so stellar, it also proved that what it wasn't able to see with its wavelength range. So it actually saw all the way up to its capability as an instrument, which is what part of the impetus that started the work on the James Webb Space Telescope. So over here you have a fairly iconic image of Hubble. This is actually taken by from the space shuttle. Down here there's some images that Hubble has taken. The one on the lower left-hand side here is what's called the Pillars of Creation in the Eagle Nebula. This is actually auroras on Saturn, on the Saturn's south pole. And then the one over here is actually Hubble's deep field. So this was actually taken in 1997. It was Hubble essentially at that time trained its eye onto a very dark patch of sky. And a lot of people thought it was, it was slightly foolish to photograph a dark patch of sky for a long period of time. What are you actually going to see? And when the image finally exposed after 17 hours, it showed hundreds of galaxies just in that one tiny little patch of sky. So it really gave us a scale as to just how big the universe actually is. So the James Webb Space Telescope is the scientific successor to the Hubble Space Telescope. Now, Hubble is 7.9 feet in diameter for its primary mirror. Webb is quite a bit bigger than that. It's actually at 21.3 feet. So that's, if you took the light collecting area of Webb, it's actually about 6 times the size of Hubble. Hubble is also, it's about the length of a school bus at 44 feet. It's 24,500 pounds. Webb is quite a bit bigger. Webb is actually the length of a tennis court. But as you can notice, its weight is actually a little bit over half of Hubble's. And the reason for that is because the Hubble Space Telescope used aluminum mostly in its construction. It was pretty rigid metal, but quite dense as well. And the Webb Space Telescope actually uses a lot of composites. So composites are much more lightweight. They still provide the same type of rigidity. So we are able to launch a much larger telescope for less weight. Hubble mostly sees it actually sees a little bit beyond what your eyes can see. So it views in the ultraviolet, the visible, the near infrared. Webb is actually stretched much further out into the infrared. So it's visible to mid-infrared. You can see the wavelengths out there. And Hubble is actually about 350 miles over your head right now. So it orbits Earth. It's fairly low in Earth orbit, whereas Webb is actually about 1 million miles away. So it's it orbits the sun around a point called L2, and it's 940,000 miles away from Earth. And Hubble operates roughly around room temperature or so. It's about 70 degrees Fahrenheit, 21 degrees Celsius. Whereas Webb, you can see the temperature there, it's about negative 370 degrees Fahrenheit. So I just gave you a lot of numbers, right? But it doesn't give you a good idea of how big Webb actually is. So, like I mentioned a little bit earlier, JWST is actually, it's about 6 times larger than Hubble. Its sun shield is about the size of a tennis court. And then if we're standing at the bottom here and you look all the way up, it's actually, the height is about the height of a 3-story building. So this is a picture of a JWST mock-up at NASA's Goddard Space Flight Center, and this is just a little part of the Webb team, actually. The total Webb team is about 20,000 people. So what will Webb do? Well, Webb is going to study every phase in the history of our universe. So it's going to start from the very, very early period of our universe, right after the Big Bang. So after the Big Bang, for about the first 100 to 250 million years or so, it was kind of this primordial soup of elements. It was very opaque. If you stood in the middle of the universe after the Big Bang, you wouldn't actually see much. And then about 100 million years after that, something pretty miraculous happened. So the first luminous stars and the first luminous galaxies started turning on in the universe. And we want to use Webb to actually be able to see that happen. We also want to see the assembly of galaxies. So at the beginning of the universe, that there were galaxies that were just small clumps of stars. But quite a bit later, we see all these, really beautiful shapes, right? The spiral galaxies, the barred spiral galaxies, elliptical galaxies. So how did they get to the shapes they are now? And we want to understand galaxy evolution, the evolution of galaxy shapes. We also want to see the birth of stars and planets. So that third picture there is actually the Carina Nebula. It is a stellar nursery, so it's a place where baby stars are born. And you can see all of this dust. Now, I mean, it looks beautiful, but all that dust is obscuring all the stars that are being born behind it as well. And with Hubble, you're able to get that image, but with Webb, you're actually able to peer through that dust to see the heat from the stars being born. So that is one of the things that we're really hoping to study with Webb. And then finally, the fourth one is actually the one that excites me the most. So we're able to see both planets in our solar system, as well as exoplanets. So planets that are orbiting other stars outside of our solar system. And we're able to peer into their atmospheres and see, right, do they have water vapor? Do they have carbon dioxide? Do they have oxygen? Do they have the things that can be used to determine if life is there? So why is all of this important? Well, JWST really helps us answer two major questions. And these are questions that we've had since the dawn of humanity, right? Ever since we've had human civilization, we want to be able to answer these questions. What happened at the beginning of the universe? And then, are we alone in the universe? Let's talk a little bit about engineering. I'm an engineer, right? So I like to talk about engineering. I gave you quite a bit of science so far. But with all the great science that we want to achieve, they do come with really great engineering challenges as well. And to be able to see all those things that I just showed on the last slide, Webb needs two things. It needs to be able to see extremely far, and it needs to be able to observe in infrared light, so it needs to be very, very cold. Now, for those of you who aren't familiar with infrared, I'm just going to give you like a quick 1-2 minute version of what infrared is. So what your eyes are able to see is the visible spectrum down there in blue. Right, this is the colors of the rainbow, red all the way up to violet. And what infrared really is it's just a longer wavelength than what your eyes could see. So if you took a picture in a visible spectrum, right? Any camera takes a picture in the visible spectrum. So if you took a picture there, you would see that person with a plastic bag over their arm. But if you took it in infrared, what infrared is essentially it's heat. So your body perceives infrared as heat. And what you're able to see is their arm behind that plastic bag there, because it detects the heat from their arm rather than just takes a picture of whatever it sees invisible. So why do we want this for Webb? Right. Well, infrared observations, they allow us to see the heat coming from the distant objects, including the first stars and galaxies. And then it also allows us to peer through those dust clouds to actually see stars and planets being born. But because we're trying to detect the faintest stars and galaxies through their heat, we really don't want James Webb's own electronics heat to swamp our measurement. So that's why the telescope has to be extremely, extremely cold, right? If all of your electronics are producing a lot of heat, then unfortunately, that's all you're going to be able to see with your telescope. Now, I gave you a couple of kind of qualitative figures in the last slide about being able to see extremely far and be able to be extremely cold, but that doesn't give you a good idea of the quantity of how far we need to be able to see and how cold is very cold, right? So how far does Webb need to see? To observe the first luminous objects in the universe, it has to be able to see up to 13.6 billion light years away. So that's equivalent to 79 billion trillion miles. And a figure like this, right, it's not something that you typically deal with on a daily basis. So a good way to relate to this is that if you scaled that between the distance between the Earth and the Moon, and your eyes had the resolving power of the James Webb Space Telescope, then you would actually be able to see a bumblebee on the Moon, both by the heat that the bumblebee itself creates, as well as the reflected sunlight from the bumblebee. And then, right, the other question is, how cold is very cold? So in the center of the slide here, I have 3 separate temperature scales, and most of you are probably familiar with Fahrenheit. Fahrenheit is, it's what the weather is reported in, right? And Celsius is really what the rest of the world uses. So Celsius is just pegged to water. It's about 100 degrees Celsius for boiling water, 0 degrees Celsius for freezing water. So Kelvin is the same scale as Celsius. It is just pegged to the coldest temperature in the universe, which 0 Kelvin is negative 273 degrees Celsius. So starting off with a reference point, right? We have boiling water here, 100 degrees Celsius, 212 Fahrenheit, 373 Kelvin. Room temperature, what we're all sitting in right now, is 295 Kelvin, 22 degrees Celsius, 72 degrees Fahrenheit. So if you were to freeze water, right, 0 degrees Celsius, 32 degrees Fahrenheit. And then let's start getting a little bit colder than that. So your freezer at home, right, it's about 0 degrees Fahrenheit. The coldest temperature on Earth is ever recorded was at Vostok Station in Antarctica. So it was about negative 129 degrees Fahrenheit. But JWST is actually quite a bit colder than that. So let's go to Mars, right? The coldest temperature on Mars is negative 195 degrees Fahrenheit. Still, JWST is colder. Coldest temperature on Pluto is negative 387 degrees Fahrenheit. Still warmer than JWST. So the average instrument temperature on the James Webb Space Telescope is negative 396 degrees Fahrenheit. And the coldest instrument, the mirroring instrument on JWST, is actually negative 449 degrees Fahrenheit. So that's 6 degrees above the absolute coldest temperature you could ever get to in the universe. So I like the scale in the previous slide, but I also really like this one. And this just gives you an idea of what would happen to your body at different parts of this temperature scale here. So how do we build a telescope that can both see extremely far and achieve very cold temperatures, right? Well, first, you build a giant mirror. You build a beryllium mirror with 26.3 square meters of light collecting area. You coat it in gold to be reflective in the infrared. Gold is actually great to reflect infrared. And even though you see these really big, beautiful, golden mirrors on James Webb, there's actually about a golf ball size worth of gold spread over all the mirrors. So it's really, really thin. It's a really, really thin layer across all the mirrors. Then you place it very far, right? So you take it, you put it around a point called L2. It's 4 times the distance from the Earth to the Moon. And then you build a giant sun shield with 5 separate layers to block light and heat from the sun. And you're blocking heat from the Earth too. You're blocking heat from the Moon. That sun shield, if you were to, equate it to sunblock, would be an SPF of about 1 million or so. And then whatever remaining heat you have, remember I talked about that electronics heat, whatever remaining heat you have, you take big thermal radiators and then just point it towards deep space, which is extremely cold, and then you reject the heat out that way. So now that I talked about some of the major components on the telescope, right, this is what we actually call them in engineering terms. So this is actually the bottom half of the telescope. This is the sun-facing side of the telescope, and this side always faces the sun, so that the telescope itself on the other side is always cold. It's always in the shadow of the sun shield. So you can see this big sun shield here. This is what we call the spacecraft element. So it has the sun shield. It has the spacecraft bus, which is this, that rectangular structure there. It that hosts a lot of the communications, the structural elements to keep it rigid when it's launching, and then propulsion components to keep it in this right place in space. And then it has these big solar panels as well, so that we get enough power for our instruments. So if you go to the other side of the telescope now, this is the optical telescope element. So it has 18 beryllium mirrors there. It has a secondary mirror on the tripod over there. And then when we go to the back of this here, this is the composite structure that actually holds the 4 instruments within James Webb. So we call this the Integrated Science Instrument Module. It has the mid-infrared instrument, the near-infrared spectrograph or near-spec, the near-infrared camera or near-cam, and then the Fine Guidance Sensor or FGS. And we really love our acronyms at NASA, so we took OTE and then we added it to ISIM and we called it OTIS. So you're going to hear a lot more about OTIS in a little bit. Now, JWST took about 25 years to develop, and there were a lot of news articles that came along the way that said, I can't believe it's still not done yet, right? So what took so long to actually develop? Well, if you start all the way on the left-hand side of this chart here, right? You start at 1996, and at 1996 is when approval went ahead for what was called the New Generation Space Telescope at the time, or NGST. So a lot of early concept studies for JWST happened in this region, roughly here. They were scoping out the technologies that they needed to develop. They were trying to figure out who was going to build what instrument. And then around the early 2000s was when a lot of the contracts started coming together for these separate instruments to be built. So NIRCam was designed and fabricated at the University of Arizona. The prime contract for JWST went to Northrop Grumman, went to TRW at the time, it's now Northrop Grumman. NIRSpec was designed and fabricated at ESA. MIRI was designed and fabricated as a collaboration between the European Space Agency, the European Consortium, and NASA. And then FGS NIRIS was designed and fabricated at the Canadian Space Agency. As we progressed forward through the early 2000s, there were 10 technologies on Webb that actually had to be developed that did not exist back in 1996 so that Webb could become a reality. So I'll give you just a really quick example of one of them. JWST has these, this very, very large mirror, right, made up of 18 separate segments. In 1996, the best mirror technology that we had at that time was the technology on Hubble, which is made from a technology called ultra-low expansion, or ULE glass. So, ULE glass is great. It's very, very heavy, though. It doesn't work much under cold temperatures, but it's very, very heavy. And if you were to take ULE glass and just scale it up to JWST's size, unfortunately, it would be too heavy for any rocket to actually launch. So we decided, okay, well, beryllium is a great material, it's lightweight, right? Let's make a beryllium mirror. The problem was that even if you took a beryllium mirror that large, it would still be extremely difficult to launch. And so you have to find a way to lightweight it, right? A lot of that technology was actually to figure out how to lightweight the beryllium mirrors so that you could actually launch them while making sure that it gets to the right shape at negative 396 degrees Fahrenheit. So what happens when things cool, right? Things start warping. And what they had to figure out was how to make the mirrors the exact wrong shape at room temperature so that they could make it the right shape at these cryogenic temperatures. So that was just one of the technologies, right? There's 9 other ones that were invented for JWST. Towards around the late 2000s, early 2010s, we had a lot of design reviews for JWST. The composite backplane, that structure there, started being fabricated. We had our critical design review in 2010, and then things started coming together after that. So we had all the instruments being delivered to Goddard, NASA Goddard in Greenbelt, Maryland. Between 2013 and 2014, we had our primary mirror segments that were delivered at that time as well. They completed the spacecraft element. And then if you took all of the instruments and then put it together with all the mirrors, then you get OTIS. So in 2016 is when OTIS became an actual assembled element. And then we flew it down to Houston at that time, and we did a cryogenic vacuum test on it at Houston. We put it into the largest cryogenic vacuum chamber in the world. After that finished, we delivered it over to Northrop Grumman, and then we mated it with the sun shield and the spacecraft element, and it became the James Webb Space Telescope. I want to draw your attention to just some of the tests that happen down here as well. So at every single step of the way, we have to test it to make sure it works. So you can just see some of the test campaigns and how long they actually took. Now, what kind of tests do we need to do? We had to do what's called a shake and bake campaign on JWST. So shake means vibrational testing, right? You're putting it on a big rocket, you're launching it, it's going to shake quite a bit. So what we had to do was we took JWST, we put it on the biggest shaker table in the world, and then we just shook it at the right frequencies that simulated the rocket launch. And the point of this is that, right, if you're shaking it at those frequencies here on the ground and something breaks, then you have the possibility to fix it, right? Because after it launches, there's not really much of a possibility to fix it. Then we put it into acoustic testing chamber. That's the acoustic chamber at NASA Goddard. There are 2 different acoustic horns on that chamber. There's one that's out of view on the bottom there, and then one that you can just slightly see, and that's actually the largest subwoofer in the world. So we launch it, or we test for the sounds of launch, right? So all the acoustic pressure, we blast it with sounds and make sure that it can survive the sounds of launch. It goes actually up to 120 decibels. And then we do what's called thermal vacuum testing. So we put it into a chamber and we want to test it at its intended space environment. We want to be able to get it to the right temperatures that it will see in space to make sure that everything works at that temperature. So this is mainly what I was involved in with my role in the James Webb Space Telescope. And I'm just going to spend the rest of these slides just talking a little bit about that. Right, so first off, how do you test for a thermal environment, right? You have to first understand what kind of thermal environment you're going to see in space. So this is JWST out in its spot in L2, 1 million miles away from the Earth. The sun-facing side of James Webb is actually very, very hot. It's greater than 350 Kelvin, which is about 80 degrees Celsius or so. The cold side, after all those 5 layers of sun shield, it's actually at less than 50 Kelvin. So it's negative 220 degrees Celsius. So hotter than Death Valley on that side, or colder than Antarctica on this side. And then you're trying to get all these instruments really, really cold. So you can see some of these temperatures down here, 6 Kelvin, 35 to 42 Kelvin. But you also have a really, really warm electronics compartment over there. So it's like, that's pretty much the computer that is able to provide power to the instruments as well as read out all the data coming from the instruments. So why do you think you want something that hot on the cold side of the telescope? So the reason you want that there is that it's close to all of the instruments to be able to read out. But actually thermally, as a thermal engineer, that is the absolute worst decision that they could have made for the James Webb Space Telescope, because you're essentially putting this extremely, extremely warm component where you want to make things very, very cold. So that actually led to a lot of different engineering challenges that we had to overcome when designing James Webb. But that's a great example of an engineering compromise too, right? So you want to keep the computer that reads out all the instruments really, really close. James Webb has to actually deploy, so you don't want all the wires to snag on anything if you're deploying that out. But then, unfortunately, in this case, thermal had to take the hit. So how do you simulate something like that here on Earth? Right? You take the cold side of the telescope, so OTIS over there. You you put it inside one of the largest thermal vacuum chambers in the world, which is NASA Johnson Space Center's Chamber A. You take out all the air from it, so you reduce air pressure to 1/1 billionth of atmospheric pressure. You take a gaseous helium shot to take the temperatures down to 20 Kelvin, or negative 250 degrees Celsius. And then you put in an LN2 shroud around it, a liquid nitrogen shroud around it, just to take the heat off of the helium shroud. So it actually, inside the chamber, it looks a little bit like nested Russian dolls. But unfortunately, even this chamber, which is 55 feet in diameter and 8 stories tall, it was not large enough to test all of James Webb in there. So what we had to do was we had to install what's called ground support equipment, which is just things that won't fly in space, to simulate the heat from the other parts that were missing in the test. So that when we got our data from the test, we can then put it into our models and make sure that everything worked out well. So really, the first test of JWST as a fully completed system was after we launched it, after it went out to space. But you heard me talk about how we had to take all the air out of the chamber, right? So how do you cool without air? No air means that JWST can't rely on convective heat transfer to cool. So it can't cool through just normal means, right, an air conditioner or anything like that. And it needs to rely on radiative heat transfer to release its heat to the space environment. So you could think of radiative heat transfer as when you place food under a heat lamp, for example, or what happens to the inside of a car in a parking lot on a hot day. in JWST, or in the test, JWST then just took all of its heat, radiated out to the cold chamber walls, and then it had specialized thermal straps to pull out its heat, to siphon out its heat through thermal straps. And what we were trying to achieve with our test was to simulate on-orbit conditions for optical testing. So we want to make sure that whatever we're trying to see with James Webb does work at those temperatures. We want to be able to ensure hardware integrity on temperature transitions, right? We don't want to break anything while it's cooling. We want to be able to make sure that our models are predicting correctly, and then we wanted to ensure workmanship in the intended environment. In preparation for OTIS, many engineering models had to be created, and there were a lot of simulations that were made. And the work for the OTIS test started in 2008 for a test that happened 9 years later. There were models that span a lot of different disciplines, right? Contamination, because you want to make sure that you get to the right, you don't have a lot of contaminants that are sinking onto your mirrors. Mechanical models to make sure that everything fit. Optical models to make sure that it was seeing what it needed to see. Thermal models to actually make sure that it could be cooled in the right way. And we also use these models to figure out how best to cool it without breaking anything. And along the way, we had tons and tons of risk reduction tests at every single step of the way to make sure that we could still be able to achieve those temperatures with every single new element of the telescope, and that our models were predicting correctly. So this just gives you a kind of an idea of all the tests that we actually had to do to get to the OTIS test. And then on the right-hand side was, that's a temperature plot showing the final cool-down profiles and warm-up profiles for how we cooled and warmed the telescope. So that took about 3 years to develop. So finally, from July to October of 2017, we were able to push the completed OTIS into the thermal vacuum chamber at Houston. That test took about 100 days. It took 32 days to cool down, and then warm up took 20 days afterwards. I like to think of it as trying to freeze and then warm the world's largest turkey. And our models actually predicted this pretty well, so we were able to keep it pretty safe. There were about 1,000 different rules that we had to make sure we didn't break, so that we didn't break the telescope, and we did pretty well. I mean, it's flying up in space now. It also required monitoring by a team of about more than 100 engineers and technicians 24/7 throughout the duration of the test. And we monitored all the test hardware, as well as we turned the right knobs to make sure that we were cooling correctly. But even with all of our planning and preparation, we couldn't fully anticipate all the surprises that a 90-plus day test in Houston during the summer would bring us. So, we're down there in Houston at the Johnson Space Center, and then on August 21st of 2017, just after we finished cooling down the telescope, we noticed in the weather reports that there was a disturbance in the Gulf of Mexico with a greater than 60% cyclone formation chance. So this was Hurricane Harvey. It happened from August 25th to August 29th of 2017. There were 51 inches of rain that were actually dumped on Houston at that time. It actually was the most costly storm in US history. And this is when we were testing James Webb. There were, so just a couple of pictures from the storm, right? There were strong winds as Harvey hits Clear Lake, Texas. And then there was a lot of flooding in the parking lot right outside of the chamber. You can see that it's a 1960s era building. Unfortunately, it has leaks. So there was a lot of water damage in our test room. Actually, we had to tarp over a lot of the electronics to make sure that they didn't break. One of the things that I didn't appreciate about hurricanes was that every single time an arm of a hurricane moves through, it can spawn tornadoes. So there was quite a bit of tornado damage, as you can see in the upper hand picture there. But even testing in our very small isolated bubble in Houston, we were still pretty keenly aware of what was going on in the outside community. And a lot of people, they lost their homes, they lost their livelihoods, some of them even lost their lives, unfortunately. So after the storm, just to give back to the community that welcomed us for so many years of OTIS testing, we actually, there were a lot of members of our team that actually volunteered for the post-Harvey cleanup. So we tested through the hurricane. We rode through the hurricane. We tested afterwards our optical tests. We warmed up the telescope for 20 days. We repressurized the chamber. And then after all of that, we opened up the door and we pushed the telescope out. and there's this really beautiful gleaming telescope that's fully tested and ready to be integrated with the rest of the spacecraft. So this is just a GLAMOUR shot post-test. You can see all of our team here lined up to take pictures with the telescope within the clean room. So finally, after the test, we transported it to Redondo Beach, California. At that time, the spacecraft element, the sun shield was also being tested. Then we put the OTIS and the sun shield and the spacecraft element together in August 2019. That completed the assembly of the JWST Observatory. We took all of that and we shook it again and we put it through acoustic testing. We did a final sun shield deployment in December of 2020, and then we made sure all the electrical connections were correct in May of 2021. So after all of that, after the final tests and everything, we actually put it on a barge. We sailed it down the west coast of North America, went across the Panama Canal, and then then went through the north coast of South America to get to Kourou in French Guiana, which is actually where the telescope was launched. It was folded up to fit inside the Ariane 5 launch vehicle. That's actually what it looks like. We like to call it the world's most complex piece of origami. And it launched on October 12th. It arrived in Kourou at October 12th of 2021, and it launched on Christmas Day of 2021. It then journeyed 940,000 miles out to L2, and through that time it actually went through 178 separate motions to unfold it in space while it was launching. So this just gives you an idea of how it unfolded. You had this the solar rays that came down there, the antenna. We had these sun shield pellets that came down. The top half of the telescope deploys for thermal cooling. And then you have these sun shield covers that actually open up on either side of the telescope. So what you're seeing here is the mid boom, the port mid boom that's actually pulling out the sun shield on one side. Then there's the starboard mid boom that actually pulls it out on the other side, and then it gets tensioned like a sheet. Right, and all of the separate layers of JWST are then popped open so that it can actually begin thermal cooling. So after it gets to about this point or so, after all the sun shield is deployed, what happens is the secondary mirror, that tripod that's up there, actually comes down and it's able to reflect what the primary mirror has. And then the two sides of the primary mirror come in, and voila, you have a completed telescope. A couple of pictures from our commissioning. This is when it separated from the Ariane 5 launch vehicle. This is actually the last picture we have of JWST. This is the Mission Operations Center in Baltimore. And then over there, you have everybody cheering. Of course, it's in the middle of the pandemic still, so everybody's wearing masks. But you have everybody cheering at the final deployment of JWST. Some of the highlights also from commissioning, we had to align all the mirrors after it deployed. So we took a star and then we actually ended up trying to align everything to the star. And once it was aligned, of course you can see the star really well. But what was unexpected is that you could actually see all the galaxies pop out in the background as well, and that just speaks to how powerful the telescope is. We released first images on July 12th of this year. This is what's called the cosmic cliffs in the Carina Nebula. Probably saw that as the background to Ashley's show. And then one of the things I was really excited about was that we also were able to see the composition of an atmosphere for a planet that's beyond our solar system. And then we just had a lot of early release science, right? So we had pictures of the Phantom Galaxy. We took a picture of Jupiter with different auroras. We took a picture of Neptune with its rings. And then also just different profiles of another exoplanet. This is called HIP 65426b. And we can understand so much about different exoplanets and what their composition is just from the pictures that JWST takes. So with that, I'm going to conclude my talk here. Thank you so much for your patience. I know it's quite a number of slides to go through. And of course, I'd like to thank Ashley Zelinskie as well for working with the Webb team to realize some incredible works of art. Of course, if you have any questions.